Thank you very much. So this talk is about the simultaneous measurements of the sound velocity and the density of liquid, and we report the effect of pressure on these properties of liquid iron nickel silicide to give a constraint of the core composition of the small bodies such as Moon or Mercury. And as previous speakers mentioned, that the possible light elements in the core can be estimated by matching the observed seismic data with measured sound velocity and density of liquid iron, iron alloys under high pressures. So this is the summarized reported results of these properties of solid iron alloys. And you can see if the light elements dissolve into the iron, the density and the sound velocity changes depending on the alloying element. But for liquid phase, there are several reports. So this is the summarized reports results of the density of liquid FES, and this is liquid FESI. So as a function of pressure. So you can see if the sulfur dissolves into the iron, density decreases significantly, but silicon only reduces moderately of the density of liquid iron. And you can also see the slope, compression curve is quite different depending on the light elements. And this is the P-wave velocity as a function of pressure, recently reported by the Jin et al. And you can see that if the sulfur dissolves into the iron, the sound velocity decreases significantly with increasing the sulfur content. And the slope also changes. So the light elements changes density and sound velocity of liquid iron significantly. But we need to simultaneously measure simultaneously these properties to obtain the precise batch plot for the liquid material. Therefore, in this study, we developed the simultaneous measurement system of the sound velocity and the density for liquid material. And we report the effect of pressure on these properties of liquid iron nickel silicide to constrain the planetary core compositions. So basically, the sound velocity was measured using the ultrasonic pulse echo overlapping method. So in this method, the transducer was attached on the backside of the anvil, and this transducer generates the ultrasonic wave signal. And then the echo signal from the sample front and sample back was detected using the oscilloscope like this. So the time difference between these two signals corresponds to the travel time of the wave in the sample. So then we can calculate the sound velocity of the sample. And the density was measured using the X-ray absorption method. So from the intensities of the incident and the transmitted X-rays from the sample can be measured and was measured. And then we can obtain the absorption profile like this of the sample. Then we fit this absorption profile using the Lambert-Bell's law as shown here. Then we can obtain the density of the liquid. Or alternatively, the density of the liquid can be also measured from the volume data, volume measurement under high pressure based on the X-ray CT measurement at high pressure conditions. So this is the CT data of the sample. It doesn't work. Okay. So, so this is the experiment, more detailed experimental setup at relatively low pressure range up to 1 to 2 GPa. So much less pressure than the previous talks. But this is the experimental setup. So we have used 80-ton uniaxial press installed at the CT beamline at Spring 8. So this press has a wide opening angle for the CT measurements. And the sample cell was located in the middle of the press. And then the monochromatic X-ray comes from this direction. And the X-ray radiography image was collected from 0 to 180 degrees by rotating the press for the CT measurements. And we also attached the transducer backside of the anvil for the ultrasonic measurements. And this is the cell assembly. We have used opposed cupped type anvil, and the sample was iron nickel silicide, nickel 10 weight percent. We changed the silicon content from 0 to 30 atomic percent. And this sample pellet was sandwiched by the single crystal sapphire buffaloed. And these are the experimental conditions of this setup. And then at higher pressure conditions, we have used a cubic multi-anvil press at BL22 XU beamlines. Last week, we just installed the imaging system of these beamlines, so it works quite well. And so this is the schematic image of the system. This is the cell assemblies. And, and this is the cubic, the tungsten carbide anvil. The edge size of the anvil was 6 millimeters. And the monochromatic X-ray of 35 keV goes through these directions, and the incident X-ray and transmitted X-ray from the sample was measured using these ion chambers for the density measurements. And the transducer was attached on the backside of the anvil and connected to the waveform generator and oscilloscope for the ultrasonic measurements. And this is the cell assembly. So in this setup, we have used iron nickel silicide silicon is 20%, and we have performed the experiments up to 4 GPa in this setup. And we also performed the experiment ultrasonic measurements using the Kawai type multi-anvil press for the iron nickel sample up to 6 GPa. So this is the results. So this is the sound velocity as a function of pressure. So this black square shows the sound velocities of the iron nickel, 10%. And this black line shows the difference line of the pure iron reported by Jin et al. And you can see the ultrasonic, the sound velocity of iron nickel locates quite close to the iron, but slightly, that allowing nickel slightly decrease the sound velocities. And this blue symbols shows the iron nickel silicide. The different symbol shape corresponds to the different silicon content. So when we see here, this is 10 weight percent, this is 20% silicon, this is 30% silicon. So you can see, if you can clearly see that the sound velocity of iron silicide increases with increasing sulfur content. And also comparing with the iron nickel, this iron silicide locates above these data points. Therefore, the silicon rises the sound velocity at these pressure conditions. But the effect of pressure on these sound velocity are quite small. In contrast, if we, these red symbol shows the results, previously reported results of the iron sulfide liquid reported by Nishida et al. And Jin et al. So if the sulfur dissolves into the iron, the sound velocity decreases significantly, as I mentioned in the previous slides. So we confirmed that the silicon, it is confirmed that silicon and the sulfur have opposite effect on the sound velocity of liquid. liquid iron and iron nickel in this pressure range. So it's quite interesting. It's a quite opposite effect on the sound velocities. And this is the density. We only obtain these data points, but these are the 20%, this is 30%. So of course, the density of iron nickel silicide decrease with increasing silicon content, but the effect of pressure on the density of iron nickel silicide is quite small. It's almost parallel to the ion compression curve. Therefore, which means that the iron nickel silicide has is very incompressible compared to the iron sulfide liquid. So then using these data, we plot the Barchi plot. This is density and this is sound velocity. Our data locates here. This is 20% silicon, this is 30% silicon. And silicon dissolve, rise the sound velocity and decrease the density. Therefore, the increasing silicon content shifts toward the upper left side in this Barchi's plot. But as I mentioned in the previous slides, in the previous slides, the effect of pressure on the sound velocity and the density is quite small. Therefore, in the present pressure condition, we cannot obtain the slope of the Barchi's plot in this of the iron nickel silicide in this Barchi's plot. So this is the implication part. So we calculate the iron and FES using we combine the FES results obtained from the separate measurements. So this is the FES, this is the FE, this is the present results. And we plot at these lines are calculated results at the lunar core conditions. So in these lunar core conditions, the effect of silicon and sulfur on these properties are quite different at lunar core conditions. Therefore, if the sound velocity and the density of the lunar core is obtained, the light elements in that core can be strictly constrained, because if the lunar core is sulfur rich, the density is quite low and the sound velocity should be quite low. But if the lunar core is silicon rich, the density and the sound velocity should be much higher than the sulfide core. Therefore, but at higher pressure conditions, the difference between these sulfide and silicide is expected to become less. Therefore, in this condition, we can give a better constraint on the core composition. So this is the summary of this talk. Thank you very much.
Any question? I can start with one. How far you can imagine pushing the press to get pressure higher than 4 GPa where you have data?
Using the cubic ambient.
Yeah.
Cubic, in this system, we can reach up to 7 GPa. But if we use the Kawai type ambient, we now developing the Kawai type simultaneous measurement system, and we plan to go to around more than 10 GPa.